Welcome to Lab LC2, the Mirrors and Lenses Lab. Students in this lab usually are able to remember the important equations. 1 over p plus 1 over q equals 1 over f. 1 over p plus 1 over q equals 2 over r. They do have problems seeing the optical effects that we would like them to see. Perhaps the simplest way to estimate the focal length of a converging lens is to hold it approximately one focal length away from the lab table. If you do this under a fluorescent light in the ceiling, then when you have the lens about one focal length away from the lab table, then you should see a recognizable image of the fluorescent lights appear on the table. This will surprise most students who are not used to images being formed without the use of electrical power, and it's important that this be done early on in the lab so they get used to seeing things with their own eyes and without preconceptions. Also, one can estimate the focal length of a concave mirror by noting the distance at which the image it forms goes from being upside down to being right side up. The distance that differentiates those two conditions is the focal length. So this can be done at home with spoons. The focal length of a typical teaspoon I estimate to be 2 or 3 centimeters. Parallax refers to the motion of the object relative to the image as perceived by a moving observer. So in this image, which shows a pointed stick in front of a large concave mirror, you see the pointed stick coming up from below, and then the image is coming down from above, and the point on the image is directly behind the point of the object. Now as I move the camera around, then we should be able to see that the relative positions of the object and the image do not change much, though the camera moves quite a bit. What you're seeing is no parallax. That's a sign that the object is at twice the focal length from the mirror. That is, it is one radius of curvature away from the mirror. Now if I move the object so that it's at a different location relative to the mirror, then I may find that I can line up the object and the image as seen from one viewpoint, but if I then move the viewpoint, then the object and the image do not follow each other. So in this case, the object moves a lot more than the image does. That's a sign that the object is further away from the mirror than the radius of curvature. Similarly, if the object were observed to move less than the image, then the object would be too close. Here we have the tip lined up with the focus, and if the eye is moved back and forth, then there is only a small parallax of the image of the tip moving with respect to the crosshairs. If the tip is moved just a little bit forwards or backwards, then there's a much more obvious parallax as the eye is moved around. So this method can be used to localize the focal length, perhaps with the greatest accuracy of any of the three methods. We are confident that all parts of the lab can be done with the equipment that you're given. When it's time to find the focal length of the diverging lens, make sure to tell the students to put at least a little space in between the converging lens and the diverging lens. Otherwise, if they're too close together, an image will not be possible. So, if you do have problems, please check with Brett Unks or Jim Reardon. If there are problems with the lab manual, make sure that you note them in the markup copy at the front of the room. Thanks a lot for teaching. Good luck with Lab LC2.